Welcome to TNSTC Chennai. So in this video we are going to learn the Kepler's second law of planetary motion, which is also known as the laws of areas or law of conservation of angular momentum. So what do you understand by Kepler's laws of planetary motion? So first of all, let's come to know that how the Kepler's laws of planetary motion was born. So the Johannes Kepler published his first two laws about planetary motion in 1609, having found them by analyzing the astronomical observations of Tycho Brahe. Later on, the Kepler's third law was published in 1619. The three laws devised by him was to define the mechanics behind the motion of planets and the celestial bodies about the sun. So let's see some important aspects of the Kepler's law of planetary motion. So you can see the pictographic representation of sun and the planet system. And the first law describes the law of ellipses, in which Vp and Rp are not constant. This fact we come to know. Here Vp and Rp are the velocity and the position vector of the planet respectively. The second law is the law of equal areas, in which we get V1 R1 equals to V2 R2 equals to Vn Rn equals to constant. And the third law, it is the laws of harmonies, where the t square upon r cube equals to constant. This equation we get. So let's come to the statements of the second law. So for planets revolving around the sun, a line segment joining planet with the sun sweeps equal area in equal interval of time. Corollary, the angular momentum of the planets revolving around the sun is conserved at every point of their entire journey. So we are going to use this corollary to prove the second law of Kepler. So from the given animation and the points mentioned in the Kepler's second law of planetary motion, it is very clear that if T1 equals to T2, then from Kepler's law we get A1 equals to A2. But as we know that the area span is directly proportional to the product of velocity and position vector, since for a given time interval t, the area span is a constant, but from the animation it is clear that the position vector of a planet varies throughout its journey around the sun. Hence we can say that at each and every point it follows an inverse relation between its velocity v and position vector r, which is depicted in the upcoming graph. So this graph shows the relationship between velocity and position vector as a consequence of Kepler's second law of planetary motion. So in y-axis we can see the velocity of the planet, and in the x-axis we can see the position vector of the planet from the sun. So if the planet goes farther from the sun, that means if the position vector of the planet increases, hence the velocity decreases, and vice versa. So here we are going to see that how the second law of Kepler is derived from the concept of conservation of angular momentum. So for a planet plus sun system, from the conservation of angular momentum of planets around the sun, we can say that mv1r1 equals to mv2r2. Hence v1r1 equals to v2r2, where v1 and r1 are the velocity and position vector of the planet respectively during the time interval t1, and v2 and t2 at the time interval t2. Therefore, for a given time interval, we get v1 r1 equals to v2 r2 equals to vn rn equals to constant. Hence v1 by r1 equals to v2 by r2. So v1 r1 upon 2 equals to v2 r2 upon 2, which is the area spanned by a planet. Hence, for given duration of time from the conservation of angular momentum, we get the derivation of the Kepler's second law.